So let's start here. So what you want to do, other than curl up in a hole and die? That's not a reasonable response. Yep, C has to be magnesium, right? Because the only way I can get a Grignard reagent is I have to have an alkyl halide and I have to add magnesium to it. So Mg, since it's an MgBr, we know that the alkyl halide was a bromine. So we know that B, basically you're just, if the magnesium sticks itself between the carbon-halogen bond, to get what B is, you just have to pull the magnesium out from between the carbon-halogen bond. A can be HBr, or phosphorus tribromide and pyridine. Either one would work. Yeah. So, we have been talking about how you turn alcohols into halides. So it stands to reason that our halide, our chlorine, was probably an alcohol beforehand, right? Just, based on where we are, time and space, whatnot, right? So we can say that E was probably an alcohol where the chlorine is, right? That makes sense? So if you look at E, you can see where the Grignard reagent added to another molecule, right? Because right here, that is right there, right? So I have a secondary alcohol. I added an organometallic to something to make a secondary alcohol. What is the something? Is it a ketone or an aldehyde? Ketones plus organometallics make tertiary alcohols. So it's an aldehyde. So then the thing that the Grignard reagent adds to in D would be an aldehyde. So it's just benzaldehyde. How can I turn an alcohol into a chlorine? HCl will work. Or phosphorus trichloride and pyridine. Or SOCl2 in pyridine. So many options. See, this is why synthesis problems get so long. It was super easy to get 6 blanks in there. No problem. Next. All right, if we're going to do another synthesis problem, I'm going to give people a break here. So I'm going to get for the first thing, kind of gimme. Get a chlorine. So the OH goes away, and I get a chlorine. Well, it's a primary alcohol. So to turn it into a chloride, using HCl, you also have to use zinc chloride as well. Remember, HCl doesn't react well with just a primary alcohol, but you could also use phosphorus trichloride and pyridine or thionyl chloride and pyridine. It's really bad Z. Yeah. And then, what am I going to get for the last one here? Oh, what's that? It does not, because it doesn't do a carbocation rearrangement because it is a primary alcohol, right? I can't make a primary carbocation. So this, I'm just going to turn my OH into an I. Right, so that feels like most of what we did last time. Yeah, new stuff. Okay, so the next thing we're going to do is we're going to talk about sulfonate esters. Right, so a sulfonate ester is you've got some carbon chain R, O, and it's attached to a sulfur. And you have some different carbon chain on the sulfur. So this is a sulfonate ester. Reactivity-wise, I would say these act like a big halide. So they can do a lot of the same chemistry that we did in SN1, SN2, E1, E2 reactions in organic 1. Right. Generally, like we make these by taking our alcohol, reacting it with sulfonyl chloride and a base, usually pyridine, and that's going to make your sulfonate ester. You're just going to have your oxygen replace your chlorine. The mechanism is pretty straightforward for this. Right, so you have your alcohol and your chloride, right, and you add to the sulfur, kick off the chlorine, and then the pyridine that you have does what it's done in all of our examples thus far. It comes in, grabs, oops, it's got a positive charge in oxygen, grabs that hydrogen, and then gets you to your sulfonate ester. Above the, oh, sorry, those are two poorly drawn lone pair. That's a poorly drawn lone pair. And then my fat finger erased everything. So it's just a lone pair. I've not filled in what the R group on the sulfur is. All right, if that R group on sulfur is a paratoluene, all right, we'll call this tosyl chloride, right? So the tosyl part of it is all of that. That's the tosyl. All right, and then the chloride is pretty obviously the chlorine. And we abbreviate tosyl as simply TS. So this would be TSCl. Right? If we have a methyl, this is called mesyl chloride, and we abbreviated MS. And again, this piece here is all the mesyl part. So these two names, tosyl and mesyl, are kind of just scrunched together versions of like the full name. So like tosyl is toluene sulfonyl chloride, toluene sulfonyl chloride. So we just are like, all right, tol, and then the sulfonyl, this is the sul, so tosyl. Like, cool, that's way easier. The last one doesn't have as neat of a name. Oops. This is trichloromethyl sulfonyl chloride. When it's on something, we've already seen this, right? When it's like, when you make the sulfonate ester, it gets abbreviated TF. So this would be like TFCl, and this would be like triflate. But it doesn't have like a neat abbreviation. You're stuck with trifluoromethyl sulfonyl. So, like I said, what is nice about these is I can make them. Tosyls and mesyls I can make and isolate pretty easily. Triflate's a little too good of a leaving group. It's a little hard to make and isolate. But what you can do is, right, you can take your alcohol, you can treat it with your tosyl chloride and pyridine, and then you can make your sulfonate ester, right? This is equivalent to if you drew out the whole thing. There you go. Your methyl group on there, right? So now I can isolate this tosyl sulfonate ester, and now I can add nucleophiles to it like I was treating it kind of like a big bromine, right? So then you could do right an SN2 reaction and displace the tosyl group with, in this case, the CN and make a nitro. If you have stereochemistry on your alcohol, right, making the sulfonate ester doesn't change your stereochemistry. You don't do anything to the carbon-oxygen bond. You're only having the oxygen add to the sulfur. So, making the sulfonate ester, you keep your stereochemistry. Right? Now when I add some other nucleophile, right, again, right under SN2 conditions, I'm going to invert the stereochemistry. Right, so I'm going to make my sulfonate ester keep the stereochemistry on my alcohol, right, because I don't do anything to the carbon-oxygen bond. Now I'm going to do an SN2 reaction with a carboxylate. I'm going to invert my stereochemistry. To get my product. Right, so we're able to make these, isolate them, and then use them as electrophiles for any number of substitution reactions. Right, so we're not just limited to always just turning our alcohol into a halide. If we make it a sulfonate ester, we can kind of turn it into any number of other things. Now there is one thing, your homework loves this, but you can, if you say like methyl or tosyl chloride and pyridine, you can in a single step turn your alcohol into a chloride, right? So if you think about what happens in the reaction, right, you turn your oxygen into a good leaving group and you generate chloride, right? So the Cl from the methyl or the tosyl gets spit out. Now it can be a nucleophile, and it can then add to the carbon that has the methyl group or the tosyl group and make a chloride. Personally, I kind of consider this almost like a side reaction, where if I want to turn my alcohol into a chloride, I have 3 other ways to do it. But this is a reaction that does happen. So if on a test, I'm like, yo, tosyl chloride or methyl chloride and pyridine, I want you to make the sulfonate ester. I think there's one homework question where they're like, what's the product? And it's the chloride. Because this is a thing that happens, but whenever I've seen anyone run into these reactions in real life, that ever been like, ooh, daddy wants a chloride. Like, no, I want a sulfonate ester, then I want to do something else with it. But it is a thing that happens because you do end up making a reasonable leaving group, and then the chloride is a reasonable nucleophile, and they can react. But for the most part, just think these are making sulfonate esters to do another reaction with. Seem reasonable? Little review of Organic 1, flashbacks.
The question was, how much Organic 1 do we need to remember for the Organic 2 exams?
What do you mean remember? You should have never forgot. You've never forgotten. Um, Typically, if I'm going to put a Organic 1 thing on an exam, it usually will find its way into a synthesis, and it will usually find its way either like very early on, so that if you don't know it, you can just like go to the next given structure and work from there, or it goes way at the end. So you've done 95% of the synthesis, and if you don't know the last step because it's an organic one thing, it's only 2 points and it's not the end of the world. I try not to stick it like in the middle where it's gonna like really throw you off, right? So I try to put it like either really early on so you can just be like, I'm gonna skip this one and just work from this thing that I'm given, or way at the end where you're like, okay, I did everything, I can just skip this last one. So typically organic one stuff is maybe 2 to 4 points on an exam. Deep down, I feel like you all know all this and they just give me points. Deep down, it's what I feel. But closer to the surface, I know what's up. Where I'm just like, you know what, But it's not gonna be like 20 points on the exam. It's gonna just be like old SN1, SN2 reaction stuff. So if you're gonna use your time, I would use your time studying organic two stuff. All right. Next up, esterification. All right. So this is where you take an alcohol, you added carboxylic acid, a reagent or catalyst, and you make an ester. Right. So there are two main ways that we're gonna have to do this. The first is the Fischer Esterification. This is the alcohol, your carboxylic acid, and sulfuric acid with heat. And this will make your ester. This is a catalytic amount of sulfuric acid. So even though it's a catalytic amount of sulfuric acid, these are still pretty harsh conditions, right? You throw acid into your stuff and then you heat the crap out of it and you hope for the best. Right. So when you do these reactions, the oxygen and all the carbons attached to it from the alcohol end up here, right? So you lose the OH from your carboxylic acid. So this carbon right here is that right there. So you have the alcohol side of your ester, and then you have the acid side of your ester. So you always lose the OH from your carboxylic acid. You never lose the oxygen from the alcohol. You always lose the OH from the acid. So these work pretty well on like simple acids and alcohols. right? So you're just going to lose the OH from your acid, put the oxygen from the alcohol in its place. Right? 1, 2, 3 carbons, 1, 2, 3 carbons. Same thing here. Oops. And it doesn't matter which, like, kind of how you draw it in terms of, like, hey, I put the alcohol side on the left and the acid side on the right. You can switch it around as long as everything has the same number of carbons, you're good, right? So I lose the OH and then put the oxygen from the alcohol in its place. Also, it doesn't always have to be written as alcohol, acid, product, right? You could have the acid be, the quote unquote starting material and the alcohol be the reagent, right? Still the same thing. As long as you have carboxylic acid, alcohol, sulfuric acid, and then in the same flask and you heat it, you're going to do this reaction. So it doesn't really matter how you draw the reagents, right? So the first two is alcohol, then carboxylic acid over the arrow. You can switch it and have carboxylic acid, then alcohol over the arrow. Same thing. They're all in the same flask, doing the same thing. So again, we're going to make our carboxylic acid. Or sorry, our ester. Reasonable? So I'm going to save the mechanism for this one till we get to carboxylic acid chemistry, because it's a little like out there compared to all the other mechanisms we've done for everything thus far. So we'll wait till we get to acid chemistry. Same for the next one. So you have the Fischer esterification, or you can use thionyl chloride. Right, again, our SOCl2, right? You have your alcohol, you have the carboxylic acid, you have thionyl chloride. And again, you're going to get to kind of the same place, right? You're going to get to an ester, but you're going to get here a little differently. Well, the things that are the same, right? Here you have your alcohol side, right? Same thing, you lose the OH from the acid still. So we've seen that thionyl chloride reacts with alcohols, right? But when there's a carboxylic acid, it reacts with the carboxylic acid faster. So what happens is that the thionyl chloride and the carboxylic acid react with each other. And you make an acid chloride. Now your alcohol reacts with the acid chloride to make the ester. So it's thionyl chloride plus acid, make an acid chloride. Then the acid chloride reacts with the alcohol to make the ester. So the upside of this is, right, if you have any functional groups in your molecule that can react with acid, right, like that could react with sulfuric acid, well, I don't have to use sulfuric acid. So, right, if you were trying to make this ester, right? If I tried to use sulfuric acid to catalyze this, right? Sulfuric acid, that's going to make it so the alcohol can react with the double bond, right? And you're going to do a hydration. So you're going to get like some ester, you're going to get some hydrated product where you add the alcohol to the double bond. All in all, no good, right? But if you use thionyl chloride, you're not using a strong acid, so you don't have to worry about that double bond reacting. This ester is the smell of juicy fruit gum. If anyone's ever chewed juicy fruit gum, am I like a million years old? Okay. I mean, I am a million years old. I just wasn't sure if like juicy fruit had been like, got rid of, right? If you get rid of that double bond, this is banana. So double bond, juicy fruit, no double bond, banana. The smell. Hmm? Funny story. So the artificial banana smell actually comes from the bananas we had like 60 or 70 years ago. But there was a like fungus or something, or like some disease that killed all the super tasty bananas. And all that were left were trash bananas. And so now the trash bananas, like 70 years ago, we were like, oh, we're not going to eat those bananas. Those are the bananas we have now. So there were like peak bananas that all died. And then and that's what this banana, like the artificial banana flavoring, that's what it comes from. Is that are the like now extinct bananas? Like they used to be more flavorful. Yeah, we got screwed on the bananas. So I brought this up, and then I had a student like 2 years ago who was like, actually, let me tell you the story about like crappy bananas and good bananas. And there we go. So yeah, all the good bananas died, and like we were just left with bad bananas. Exactly. That's why banana flavoring doesn't taste like the bananas we have now, right? Like you eat like a runt, and you're like, this doesn't taste like a banana. Apparently, that's what bananas tasted like. Apparently, it was just all delicious candy. It's like just pick candy and potassium for years, and then they were like, you know what? You just get potassium now, right? Yeah. And there we go. All right. So far, so good. You actually get to do Fischer esterifications in lab in a few weeks. Like you make something that kind of smells like peach. You make something that's supposed to smell like orange, kind of vaguely citrusy, and then you make the banana smell. Like, oh, yours is online. Yeah, you can pretend. Light a candle. There you go. I could go cut it in like part of the lab is go to the Yankee Candle shop, buy banana candle, light candle. I could just do that. There we go. Ooh, I could get like a sponsorship from Yankee Candle. Yeah, man. There we go. I am a pro YouTuber. I have two copyright strikes. Both of them are just me randomly talking. Remember when I drew the hydrogen bonds for ethanol? Some French educational like software or content maker copyright struck a minute of me talking about hydrogen bonding alcohols. I was like, no, I just can't monetize that video. I could dispute it, but it's not worth like my trouble. I'm like, it's just me like drawing bad ethanol. I don't know like how you can like copyright strike this. They've done it to me twice. One was when I was explaining in Organic One how to name molecules. It was like a slide and me talking, a slide I made myself and me talking. And they're like, yeah, we have the copyright on that. And I was like, did I sell out and I just don't remember? Like, what happened? Yeah, so it's a pro YouTuber lifestyle, man. It's just rough now. People coming for my paper. All right. So we can do all this stuff with alcohols, right? We can turn them into halides. We can turn them into esters, right? We can turn them into other leaving groups. What if we just want them to go away? right? So we kind of know these reactions already, right? So the dehydration of alcohols, right? So removing H2O to make double bonds, right? You may remember from organic 1 that your product is going to be determined by Zaitsev's rule, which kind of shorthand is make the most substituted double bond, right? You're going to want to make the most substituted double bond for these. So, right, the easiest way to do dehydrations is, again, throw acid at it and heat it up. You're going to remove water and make the most substituted double bond that you can. So, right, from a mechanism point of view, I don't know if I have space. We'll hope. Right, it's pretty straightforward. You have your alcohol and your sulfuric acid. You protonate your alcohol. We make sulfate. Because it's on a secondary carbon, we're going to make a carbocation before we do anything else. So our water molecule is going to leave. We make a carbocation. We have water. And now that water molecule or another molecule of alcohol that we have in the reaction can act as a base to grab a proton and make the double bond. So you can use water or you can use that alcohol that you have that you started with. Either one can use its lone pairs to remove the proton to make the double bond. That makes sense? So we can use sulfuric acid. There's one other acid that gets used a lot, and that's phosphoric acid. So, boop. Right. So phosphoric acid and heat. We'll do the same thing. Now again, as with all of these things that make carbocations, you just have to have it in the back of your head. Oh man, I might rearrange. Right, so you could make the carbocation, then do a ring expansion, Then do your elimination. And get your double bond. So there's always a chance of doing a rearrangement with these since you're going through a carbocation. Right? These reaction conditions have the same problem that all of our other sulfuric acid reaction conditions have. What if you have another functional group in your molecule that's going to react with the acid? Or what if you really want to make this, right? And you don't want to make a carbocation so it can't rearrange, right? We have to have another set of conditions to avoid a carbocation. And so the other reagent that we have that can do eliminations but doesn't go through carbocations is phosphorus oxychloride. So if we have our little example we just did, POCl3 and pyridine. Phosphorus oxychloride, POCl3. When you have the O, you make double bonds. If you just have PCl3, you just make chloride. Don't mix those two reagents up. They're only off by one atom, but they do two totally different things. I've seen too many good people go into a test and have those mixed up in their head and then get like 8 points off on the exam in various places. And I feel bad, they feel bad. So remember, O gives you double bonds. You don't know? Gives you double bond. They each have an O in the word, right? You need an O to spell double bond, right? Don't tell me about how to spell chlorine. Shh. But right, if there's no oxygen on your phosphorus, you just make a chlorine. All right, so what am I going to get for the first one? Going to replace the alcohol with the chlorine. What am I going to get for the next one? I'm just going to get the double bond. I'm going to make the most substituted double bond. All right, I'm still going to follow Zaitsev's rule. Make the most substituted double bond that I can. There we go. This next one is, I took kind of the two steps we've done before and kind of stuck them over one arrow. So step 1 makes a sulfonate ester. Step 2 then does the SN2 reaction to displace that sulfonate ester. So we're just going to invert our stereochemistry because it's an SN2 reaction. And we're going to make that ether. Great, so great, that's our step 1. That's what we get after step 1. And then we do our second step to get to our product. So we're going to start on next class by doing the mechanism for POCl3. So we'll start there, and then this is kind of the last thing before oxidation starts. So with that, I will see you guys next time.